Awesome. Thanks everyone for joining us. Happy December. We're extremely excited to have Karl here to present some of his work. This will be kind of the last seminar of the year, and then we'll take a little bit of a break in the winter, I think, and then coming back in the fall. So just a couple of quick normal announcements we have. You can see there our schedule on the bottom left. We're ending in December. We're recording this talk now and we'll upload it to our YouTube channel. So we will add that link onto our website. So come back and check it out there if you're interested. And again, if you haven't signed up for our mailing list or have a speaker suggestion, please feel free to reach out. We use that to kind of advertise this seminar, but also working groups in the summer and so forth. So please be sure to do that. So I'm very happy to introduce our today's speaker, who is Karl Laundal, who's a researcher at the University of Bergen. Karl's done a lot of research both on kind of atmospheric and hemispheric asymmetries in geospace and describing ionospheric electrodynamics using a lot of multi-data sets. And today he's going to be telling us about the model that they've been developing called LOMPE. So I will stop sharing here and let Karl take it away.
Okay, thank you. Share my talk. Do you now see the right screen?
Yes.
Yes. Okay, good. Thank you, Alan, for the introduction, and thank you very much for the opportunity to present this work here. LOMPE is something that I have worked on for the past few years, together with several people, mostly here in Bergen, listed on the first line. Some of them are still here and some of them have left. And then I would also like to acknowledge all the help that we have received from several external collaborators. So I will start by giving a kind of a background and introduce the problem that we are working on, which is polar ionospheric electrodynamics. Talk a bit in general about what observations are available and the general approach to combine them using ionospheric Ohm's law. And then I will briefly review some techniques that use ionospheric Ohm's law to combine measurements. And the last part of the talk, the main part of the talk, is about our technique to do that, which is LOMPE technique. And feel free to interrupt me with questions if something is unclear during the talk. So polar ionospheric electrodynamics, I like to, when it comes to space plasma, I like to think of main parameters as the plasma flow and the deformation of magnetic field. In the ionosphere, we talk about instead the electric field and the current, because it is convenient, but these quantities are related. So the four parameters are then the velocity, the magnetic field perturbations, and electric field and current. And in the region of the ionosphere that we are interested in here, there are two forces that are dominating, and they are the Lorentz force and the collisions between space plasma and the neutral atmosphere. I'm also going to make the assumption that the ionosphere is two-dimensional. And when you look at the ionosphere on a large scale, like this figure is to scale. And it shows actually a contour plot of the Petersen conductivity. So the more blue it is, the higher the Petersen conductivity is. And on this scale, it's really a line. So a 2D approximation is mostly okay when you're talking about fairly large scale phenomena. I'm also going to focus on this region where the magnetic field is vertical. So that's the polar regions. Things change when you come to to lower latitudes because the main field, the geometry of the main field is different. So we take advantage of the vertical field lines in what I'm going to present. So to study these quantities in the 2D ionosphere, we have a number of observations that we can use. So the one that goes that has the longest tradition, I think, is ground magnetometers. It's relatively easy to measure the magnetic field. It can be measured very accurately, and it's not very expensive. So there's a lot of stations around the world where the magnetic field is routinely measured precisely and at high time resolution and robustly. So there's few data gaps. These magnetic field perturbations, the most plain way to analyze them is in terms of an equivalent current. You can always model the magnetic field perturbations as being produced by a two-dimensional current flowing in the ionosphere. And it's common to present such equivalent current like this, equivalent current function. So here the contours represent a current that would produce the perturbation that is observed on the ground. It's not necessarily the same as the true current, that this I will get back to. The contours are such that there's a constant amount of current flowing between them. So here there will be a strong current, and here there will be a weaker current. And in these plots, I will show several plots like this. We're looking down at the North Pole. The sun is on top, midnight at the bottom, and we have dusk here and dawn here. So that's the format. These are equivalent current systems from a paper by Eigelfried-Christensen that I will come back to later in my talk. And this map is from SuperMag, which is a web service that collects different magnetometer measurements from several groups that operate the magnetometers and provide the data in a coherent format. So ground magnetometers is one way to measure the magnetic field. To investigate the ionospheric electrodynamics. Another way to investigate it is using magnetometers in space. So here is the 10-minute snapshots of magnetic field perturbations from the Iridium satellites. So there are a lot of Iridium satellites. With the primary purpose of these is to offer telecommunication services, but they also have magnetometers. And during 10 minutes, they will cover the polar region basically with magnetic field measurements. So one satellite gives the data from a different satellite is color coded. So during 10 minutes, you will get one satellite will make this measurement, another satellite will make this measurement. So they are in the same. They're flying 6 different orbital planes, and in total they will give global coverage. And then one can use this to derive field-aligned currents. So that would be the current that is flowing into and out of the ionosphere, connecting to the horizontal currents. And these figures are from Ampere, which is a project that does this with Iridium data. Another very useful data set is SuperDARN. This is a network of radars on ground that have a very, in theory, very good coverage of the polar regions, measuring the line of sight plasma velocity. So the radar here will measure the velocity of the plasma, the component of the plasma velocity along the line of sight in its field of view. And then when you combine all of this data, you can derive global convection maps. In practice, whether or not you have backscatter depends a lot on the conditions. So, the actual coverage is very variable. Here's an example where you have backscatter in these locations. And you see in the background here a global convection map that is derived from a combination of these measurements and a background empirical model. So these are three different things that give different that tell you about different aspects of the ionospheric electrodynamics. And now the question is, how can we combine them to get the full picture? So the answer to that is to use a model, and the simplest model I think that we can use, it's also a very useful model, which is the ionospheric Ohm's law. The ionospheric Ohm's law describes the relationship between a current and the electric field in the frame of reference of the neutrals, assuming that we have a force balance between plasma neutral collisions and Lorentz force. And this version of the ionospheric Ohm's law, I also have used the capital conductivities or conductances. So that means it's height integrated, and to do that height integration, we normally need to assume that the magnetic field is vertical. So there are a number of assumptions that go into this, but if they apply or approximately apply, then this is a very useful equation. So how can we use this to relate all these different quantities? The first thing to do is for the EPIT measurement to relate to this quantity is the velocity. So if you have the measurements of the plasma velocity above the ionosphere or above the lower ionosphere, where this red equation applies. So this is the generalized Ohm's law for ideal MHD. So if that applies, then we can take the plasma velocity, take the cross product with the main magnetic field of the Earth, and get the electric field. So this capital B, that's the main magnetic field of the Earth, and we get this from a model, IGRF or the chaos model, for example. The magnetic field is more tricky. So the magnetic field relates to the current, of course, and the relationship is described by Ampere's law. So this delta B is what we measure either on ground or in space. And we can use that to calculate or estimate the horizontal sheet current in this case, since it's a height integrated 2D equation. But to do that, we need also to know what is the conductance. And I'm going to assume, and all the techniques that I'm going to describe, assume that the conductance is known, or the conductance is found before we try to find all these other quantities. And that makes the problem a lot easier because it becomes linear. If we were to try to estimate the conductance at the same time, it would be a non-linear problem. So the observables are then the delta B in space and on ground, and the plasma velocity from radars or from satellites. I didn't mention that, but there are other sources of measurements, but the ones that I mentioned, these networks, they provide global coverage and are convenient to use. Conductances you can also to some extent measure, because the conductance depends strongly on the ionization rate, the plasma production mechanism. And auroral ionization is one variable and very important ionization mechanism at high latitudes. So if you have auroral imaging or measurements of the precipitation, you can estimate the conductance. So the way that we can relate these different quantities, different measurements to each other is by the ionospheric Ohm's law. So the radars, we use generalized Ohm's law and for ideal MHD. For ampere for the when we know the field line currents or the magnetic field high up in space, then we can relate that to the divergence of this current. So we have to take the divergence of this equation to relate those measurements to the electric field. For ground magnetometers, there's a Fukushima theorem which states that for vertical field lines, we can only see the divergence-free part of the horizontal current. And so by taking the curl of this equation, we can relate the measurement on ground to the electric field. This I will get back to now when I talk about the implementation. So I will start with this important paper from 1981, the KRM technique. It's referred to as the KRM technique. And they did exactly this. They took the ionospheric Ohm's law. They took the curl of the ionospheric Ohm's law to get an equation that relates the electric field to the divergence-free current, which is inferred from ground magnetometers. So they combined ground magnetometers with conductance estimates to derive everything else. Now going back then to the paper by Egil Christensen, where they derived the equivalent current systems. This was based on measurements from the Greenland magnetometer chain, which is up here from the summers of 1972 and 73. And using the KRM technique, they derived electric potentials. So that's shown to the right. So they took ground magnetometer data and derived the electric potential. You can also, of course, if you have the electric potential, you know everything here, so you can take the divergence of it, and in this way you can get the field line currents. So one important thing to mention here is that to do this, this equivalent current has to represent the divergence-free part of the current in space. But when you have a disturbance, a magnetic field disturbance in space, you will also induce a disturbance or a current below the surface. So you'll have the measurement that you have on the ground will have a contribution from both space and the ground, and you need to somehow account for the induced current or hope that it is negligible. It is small compared to the external influence, but it can still be substantial. I think this is also an important paper because it speaks to the question how to interpret ground magnetometer data. And ground magnetometer data goes back, the use of ground magnetometer data goes back a very long time, and we often see people inferring properties about field line currents. So Christian Birkeland, for example, did that 100 years ago. He predicted the existence of field line currents based on ground magnetometer data. But the measurements are ambiguous without more information. So you really have to introduce more information, for example, about the conductance or about the electric field, to be able to conclusively say that based only on the ground magnetometer data, say that that you have field line currents. Of course, it was proven correct when we had the first satellite measurements of the field line currents. So after the KRM technique, kind of expansion of that technique maybe is the AMI technique, which was published in 1988. There's a nice review paper by Gang Lu describing that. So in the AMI technique, in addition to the ground magnetometers, we can include satellite magnetometers and radar data using the ionospheric Ohm's law. And they are related using the spherical cap harmonics. That's the basis function that's used in this technique. And it's done in a two-step way. First, solve for the conductance, and then using that conductance, one can solve for the other quantities. AMGEO is kind of a further development of AMI. It uses AMI to combine superdarn ampere and supermag data. By default, they use ovation prime model to specify the conductance. They also use spherical cap harmonics. I think this was presented in the first AMGEO seminar by Tomoko. So then I come to the main topic of the talk, which is our technique that we call local mapping of polar ionospheric electrodynamics, or LOMPE. So this also uses the ionospheric Ohm's law and the same data as in AMI, but instead of spherical spherical cap harmonics, we use spherical elementary systems as basis functions. And what this does is that we can zoom in on specific regions, and we can adjust the spatial resolution of our grid depending on what kind of data we have available and what phenomenon we are interested in, and so on. And I'm going to explain a bit more how this works in the next in the last part of this talk. Like I said, with LOMPE, we specify a grid. So here is a kind of a toy example where we cover Great Britain and Ireland with a grid, and in each of these grid cells, the red grid cells here, we have a model parameter, and these model parameters, they represent the physical interpretation of the model parameters in LOMPE is that if you imagine a line that extends from the base of the ionosphere and radially out to infinity, and a charge distribution on that line, so charge per length on each of these lines, this configuration would produce an electric field. And the task we have is to find the optimal combination of charges that produces an electric field that is consistent with the observations. So the equation for that relating these charge densities to the electric field is given here. So if we have measurements of the electric field, then we would use this equation to do an inversion for the charge densities. Normally, we don't have measurements directly of the electric field, but we have measurements of the velocity and ground perturbation, ground magnetic field perturbations, or space magnetic field perturbations, like I mentioned. And then we need to use ionospheric Ohm's law to relate these quantities to these charge densities. And I'm not going to go into detail in how we do that. I would refer to our paper about this. Just I want to repeat that we have to assume that the conductance is known. So the way that it works in principle, I mean, this is also a kind of a toy example, is that you should be able to take any combination as input, any combination of ground magnetic field, space magnetic field, F region plasma velocity, ionospheric electric field, or field line currents. Any combination of this as input, and the output should be all of the above. So in this example, we've taken synthetic data from the Gamera MHD simulation. So you have the conductance here in the background, and you have the electric potential here, field line currents, ground magnetic field, and space magnetic field. And in each of these other columns, we run LOMPE with different inputs. So in this column, the input is only the electric field, and we derive everything else. In this column, the input is only the field line current, and everything else is derived. So you can see that these quantities match in a horizontal line. So we are able to retrieve the full picture of the ionospheric electrodynamics using only one of these quantities as input. But of course, this is a very synthetic example, and we never have a global coverage like this. So I'll show some more realistic examples. So here we have an example where we have the grid focused, or we zoom in on North America here. You have this thick black line, which is the bottom of each of these other plots. In this panel, we show the convection velocity and electric potential. The orange stuff, that's super darn line of sight measurements that go into the LOMPE inversion. In this panel, we have field line currents in color and magnetic field in space as arrows. The orange arrows are iridium data. And in this panel, we have the ground magnetic field. The color is the radial component, and the arrows are the horizontal component. And the orange arrows, that's supermag ground magnetic field measurements. So all these measurements are included in the inversion to derive the maps that you see in the background. And in this case, we use an empirical model at the conductance. It's a Hardy model, which is from, I think, late 80s. There are better models, and it would be better to use measurements, of course, but this is still better than nothing. So we can compare this result with what would happen if we only had ground magnetometer data. So this is exactly the same event. I can flip back and forth, but in this case, we only have ground magnetometer data. So this would be the KRM technique applied only in this specific region. Yeah, in our case, we account for ground induction by assuming a superconducting spherical shell at some depth beneath the surface. But this is the difference between the two ways, and you can see that there's of course a difference when you include more data. It looks more realistic, I think, but you get a clear idea at least of the convection from only the ground magnetometer data also here. Here's another example from an event that could be called a space hurricane. It was called it in a paper from 21 in Nature Communication, because you have this vortex, strong convection vortex. The main difference in terms of inversion here is that from the previous example is that we have, in this case, global UV images of the aurora, and that gives us a better handle on the conductance. So now it's not an empirical model, but actually derived from data. Unfortunately, it's been a long time since we had such data. This is back in 2001. And back then we didn't have iridium, so we didn't have a lot of space magnetometer data. So here it's only based on SuperDARN and SuperMag. So only ground data went into this. But this green line, that shows the CHAMP satellite that was in space at this time, and it measured the magnetic field along this trajectory. And using this ground data and the conductance and the LOMPE technique, we can predict what is the magnetic field along the CHAMP trajectory. And that's shown here as dashed lines. And you can see that we are able to predict the general shape of the magnetic field disturbances along CHAMP using only this ground data. So here's the global map with the auroral image in the background, the analysis region in red and the champ trajectory in green.
Karl, I think we have a
Yeah.
question from John. Do you want to unmute yourself and ask?
Absolutely. Thank you. Really great stuff. A question I have is, do you have a sense of what it is that drives the differences in this case between the LOMPE and CHAMP observations? Are there so I'm just curious about that aspect of this.
Yeah, so there's clearly differences in what we can resolve here. The LOMPE predictions are smoother than the CHAMP measurements. So that's of course the main the most striking difference. There are a number of things that go into a number of assumptions that we have to make that we could change and that would change our predictions. I will come back to some of them. In particular, what has to do with regularization, how we ingest information about or prior assumptions about physics to the inverse problem. So maybe I come back to that. Not this.
Absolutely.
I think that's at least will be relevant.
Cool. Thank you.
Yes. So here's also just a quick snapshot of the same analysis region as in the previous figure showing Joule heating, because this is also something that we can, of course, calculate once we have a full map of the current and the electric field. We can calculate J.E, which is the Joule heating here. Here's another example from a paper by Sarah Gasparini from earlier this year, where she used the LOMPE technique also together with conductance estimate from image FUV data to work out the convection or the convection pattern during an event with quite good data coverage. So that's shown in these snapshots here on the right side of these two columns. In this event, she also traced the poleward boundary of the aurora, which can be interpreted as the open-close boundary. And if you calculate the flow across the open-close boundary, you get the reconnection rate. So that's what she used the LOMPE technique then to calculate the reconnection rate. So this is a remote measurement from the ionosphere of reconnection that takes place on the night side in this case. This also would work on the day side if we had coverage on the day side. Here's an example from a paper that is currently in revision by Dan Billett. He has used the LOMPE technique to with a new superdarn mode that has very, very high time resolution compared to conventional superdarn data. So in this video, you can see the frames update every 3.7 seconds. So that's the time resolution of this new superdarn data that he uses. And then he used the LOMPE code to derive the flow field everywhere in this map, even though the data is only in some of the regions. And in this case, of course, we use generalized Ohm's law from the F region to relate the velocity and the electric field. And this does not depend on the conductance. So in this case, the conductance is irrelevant as long as we don't try to calculate what is the associated current here. So it's basically just fitting a curl-free electric field to the convection measurements. So in that sense, it's also similar to techniques that have been presented in other papers by Tochi Nishimura this year and Bill Bristow in 2016. The main difference is probably in the regularization, I think, which is what I will talk about next. So when we use the LOMPE technique, this is the workflow. We define an analysis grid, like I mentioned before, and then we have to define the conductance. And then in the code, we initialize the model object. We add the data in a specific format that has been prepared, and then we do the inversion. And it's always the case with real data that we never have enough data. So for example, here, from this example that I showed earlier, there are large regions where you have just no data. And if we just did a least squares fit to the data that we have, the result would be gibberish. I will show that in the next slide. So the solution to that is regularization, meaning that we have to include in the inversion knowledge or assumptions about what the solution should look like. Yeah, so once that works, of course, you have the model vector, all its charges, and then you can derive everything or calculate everything else. So to illustrate this issue with the regularization, I have an example from which is not LOMPE, but from the EASY satellite mission, but we use the same regularization scheme in EASY and in LOMPE. So EASY will measure the magnetic field along 4 lines. So that's shown here. So here I have 3 pairs of maps, and in the left-hand columns are always the same in these 3 combinations. But in this column, this first column, we just do a least squares fit to the EASY data. So we take the data that's along this path, can be seen here. We take a least squares fit to work out what is the magnetic field pattern in this region. And you can see that it's really meaningless. So probably here we fit the data quite well, but we fit every little wiggle in the data. We fit every noise, every little jump that the data makes. We try to fit that. So this is overfitting. So to prevent that, we have our default approach is to use two damping parameters, 2 ways to nudge the solution into something more realistic. So the first way is to limit the magnitude of the solution vector. So this is approximately similar to what is achieved with truncated singular value decomposition, and it leads to a smooth electric field. So that's what's shown here. So here you can see it's much better than in this column, but we get this kind of islands, patchy solutions, and we would often expect the solution to be more elongated in the magnetic east-west direction. So that's the second regularization term that we usually include, is to add a penalty to gradient in the magnetic east-west direction, and that's shown here on the right-hand side. So this result looks better than this. This is our default way of regularizing in LOMPE. But I want to emphasize that the regularization is inclusion of prior information. It's physics, and we should be critical of it. The choice that we have made is not always the right one, and we have discussed a lot several other alternatives. One alternative that I like and has been demonstrated not with LOMPE, but in papers by Clayton et al. In 2019 and earlier this year by Van Iersel et al. They had data they had measurements of an auroral arc, images of an auroral arc, and then an instrument crossing the auroral arc, and then they extrapolated the data along the arc. So instead, I mean, this is conceptually maybe similar to or east-west regularization, but instead they use they would assume then that the solution is constant along the arc instead of in the magnetic east-west direction. So if we had data like this, we could maybe instead use that information to guide the solution. And I actually recently implemented an option to do that in LOMPE, but I have not tested it. So, I think this is a promising approach if we have that kind of information. Another approach would be to minimize the difference between the solution and some empirical model. That it, I think in practice what is done in AMI. One could also take only the orientation of the structures from an empirical model and not the numerical value necessarily. So that would be one possibility. One could try to minimize the total field-aligned current. So that is also actually implemented in LOMPE. So that's an option that we have. One physics-based, I think, compelling strategy is to minimize the Joule heating. But I'm sure there are other ways to do this, and I'm very interested in new ideas. So the LOMPE code is also fairly easy to adapt if you have ideas. So the code, I have 2 slides about that, is publicly available. It's all in Python. It's well documented. There's lots of examples with how to use it. There are papers about the LOMPE concept and the code, and also on spatial resolution, which I will talk about in a minute. And it's using NumPy arrays, so it's quite efficient for Python code. There are elements of the code that are useful in other aspects as well. For example, you can use it to calculate the gradient on the grid, so that using finite differencing. Yeah, so I would refer to the paper by Amalie Hovland for more details about that. I want to talk now about the spatial resolution of the solution. So I mentioned already that we use spherical elementary systems, these local basis functions, and that we can play with the grid resolution. So depending on what problem we're interested in, we can play with what kind of grid resolution that we have. So here's an example from West Greenland. Here's from North America. Here's the high resolution grid over the field of view of the upcoming ice cat radars in northern Norway, Sweden, and Finland. But the grid resolution is not the same as the model resolution. So this is the point that I want to make in the next slides. This was discussed recently in a paper by Michael Madelaire. He used URSI as an example, but it works exactly the same way with LOMPE. He came up with a way to quantify a better metric for the spatial resolution in both URSI and in LOMPE. So he does this using the resolution matrix. So to see how that works, if we first consider the forward problem, so if D is a vector of data and M is a vector that represents the true model, these are related with the matrix G. So if you know the true model, we can get the data using the matrix G. In the inverse case, we have to swap this around, and we get an estimate of M given the data. But we can't just invert the G. We have to include in this G dagger, we have to include data covariance and regularization. So all of these things that I've discussed are included now in this G dagger. So by combining these two equations, we can find out how our estimate is related to the true model. And this gives us the resolution matrix. So here's an example where the true model is assumed to be 1 in this dot and 0 everywhere else. So the grid is kind of distributed in this figure here. So the true model is 1 here and 0 everywhere else. If you run this through the resolution model, resolution matrix, you get this red blob, and that's what you would get given in this case the data and the regularization. So that's how well we can resolve this dot. And by measuring then the size of this blob, we get a better estimate of the resolution than what is than the grid resolution. So you can see here the number of grid cells on the axis. The blob is much larger than 1 grid cell. So here's an example with LOMPE. So here's again the plot on the same format as before. You can see the orange stuff, that's where we have data. So again, here's a map of the data. And here is, like in a previous slide, if the true model is 1 on this black dot, the red blob is what we get with this data and the regularization that was chosen for this example. And the size of that red blob, that's the model resolution. And of course, that changes throughout the map. So by moving that dot around, you can work out what is the resolution at different places on this map. And it will not, the blob will not be circular, so the resolution will be different in different directions. So it's not isotropic. And this makes sense, for example, if you have line of sight data, you can resolve what's going on along the line of sight, but not across it. So you will have different resolution along the line of sight and across the line of sight. And yeah.
Oh, we had another quick question for you.
Hey, yeah. That Madelaire reference, the 2023 one, do they cover this method or simply an example of it? Is there a good reference that talks about this methodology about finding a spatial resolution?
Yeah, it's in this paper. Yeah.
It's in that paper. Okay, thank you.
One thing that I can mention about this way to do it is that they have really, I mean, we really need this particular grid to, or this kind of grid to do this analysis. So we make use of the grid to work out the resolution.
Okay, all right, thank you.
And then we had one more from David.
Yeah, sorry to interrupt. I was just because we're taking questions in the middle, I just figured I'd ask. So how does this differ from kind of conventional degree of freedom based resolution methods, where effectively the resolution is just proportional to the your grid resolution divided by the degrees of freedom within each grid box? So like the diagonal elements to your sensitivity kernel. So how would this compare to doing that in kind of the more conventional way, or is this kind of coming from a similar lineage?
I'm not sure. So I think I would refer to the paper for more details about that. I know that this technique that he worked out for this particular problem was inspired by techniques in other branches of geophysics where they do this. But I think, yeah, I would refer to that paper. I think that's, you will get a better answer there. I'm sorry.
No, it's okay. I'll read the paper. Yeah, thank you.
Yeah, so I mean the point here is at least the resolution is not the grid resolution, and the grid resolution should just be chosen so that it's not the limiting factor. Yeah. So I have one slide about uncertainty, which is more of an unsolved problem for us. We can easily calculate the model variance, but it's not necessarily easy to interpret. So the way that I think of this is the regularization. You can always increase the regularization, and that will reduce the model variance. If you take the regularization to infinity, you will always predict the model that says 0. So the variance will be very low, but it's still not a good model. I think what this reflects is that the regularization represents our prior assumptions, which can be wrong, and that's not captured in the model variance. So, of course, we can calculate the model variance. It's easily available, but it's not necessarily a good measure of the uncertainty. One possible solution that we are working on is to use OSIS. We have a project where we want to add a functionality to the LOMPE code where you can, given a real data set, create simulated copies from a set of simulations, and then compare the inversion results using this realistic data to the ground truth, which is the simulations. So maybe that's a better way to assess the uncertainty in the solution. So this is similar to what we did with EASY. In EASY, we had this global camera MHD simulations. And then we ran that, we simulated the data that EASY would measure, and then we used that simulated data to retrieve the magnetic field pattern and the electrojet pattern, and you can compare this to the ground truth, which is here. So something like this, we want to do something like this also for LOMPE. So my last slide is about future plans and ideas. We're still working on LOMPE. One of the things that we're working on in one of our projects is to include inductive electric field. So we have assumed that the electric field is a potential field. It's possible to, we want to expand that to include also the inductive part of the electric field, which is small in the ionosphere, but it contains information about how the ionosphere changes from one time step to the next. So in all the applications that I've shown, also the convection video that I showed earlier, there's an independent inversion for every time step or every time interval that you choose to select data from. But we would like to be able to connect the different time steps using physics, and I think this one way to do that is through the induction. Yeah, so I mentioned these things with alternative regularization strategies, and one of them would be to include time dependence in a new way. I mentioned the database dominant direction that's implemented but not tested, Joule heating minimization, and other approaches, possible approaches for regularization. We also would like to improve how we handle ground-induced currents by using a more realistic ground conductivity model. This also will require us to take into account the time history, because induction depends on frequency. One idea that we've been thinking about, but I'm not sure how feasible it is to include F-region density. The problem with that is that F-region density, there's a lot of data, but the plasma in the F region is so long-lived that to do that, to include that, and to get any information about the velocity from that, you would have to include the time history of the velocity for several hours. I mentioned that we make use of, or the assumption that the magnetic field is vertical. It's not entirely true, but it's mostly true. We would like to account for a more realistic magnetic field geometry that would allow us to go to lower latitudes. And then finally, we would like to co-estimate the conductance. This is super difficult because it makes the problem non-linear. We have an idea for how to do this on a global scale, and it's something that we're working on. And I may also have forgotten some ideas, but these are this is still enough to keep us busy for a long time, I think. So this is my summary. The LOMPE technique is a technique to combine different types of measurements, give a complete picture of ionospheric electrodynamics with a flexible extent and spatial resolution. You can use different input and get an output would be all the relevant ionospheric electrodynamics in 2D. Yeah, we use a cube sphere grid, finite differencing scheme on that grid, and spherical elementary current systems as basis functions. And the code is fully available. Yeah. Yeah, so thank you for the attention. I'm happy to take questions.
Thanks very much, Karl. Any final questions before the end of the hour?
Yeah, Karl, thank you very much. Very exciting. And then I really appreciate that you explained how this came about, has a long history, and it came really long way as a field. It's a, I just have a, I mean, I think you had a good questions already about like a sort of boundary effect. How would you see that, you know, like it's a, you have to set up the grid, you know, regional, and then how would you envision to sort of do global merging or something like, you know, it's like I'm just thinking like from my perspective, we have I'm more, you know, focus on global aspect, and you have some.
The boundary conditions is it's a very good question, and something that I should have put on a previous slide, I think, in like future work, because we don't have an explicit boundary condition in LOMPE. So but it doesn't mean that we're unaffected by we're solving essentially boundary value problems without specifying the boundary. This works well in some cases, but it's easy to envision scenarios where this would blow up. For example, if you have magnetometer data in a region that's very dark, the LOMPE technique would try to explain any perturbation using currents inside that region. And if it's very dark, the conductivity is very low, so the electric field that would be needed to explain that magnetic field observation would have to be very, very large. So one way to account for this that we have thought about and would like to explore is to use something like AMI as a pre-processing step, where we try to account for the large-scale structure, and then use LOMPE to model only the high-resolution residual. I think this would this sounds promising to me, but we have not yet tried it.
Thank you.
Any other questions?
If not, let's thank Karl again for the wonderful talk. We will be uploading this to our YouTube channel very soon. Yes, virtual virtual applause. And thanks all for attending. I wanted to correct, we are looking for speakers in both February and March, so be on the lookout for those updates to our schedule. And we hope everyone has a great December, and we will see you in the new year.
Thank you.
Thank you.
Thank you. Bye bye.